go. I just hit record. Check, 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 check. There's sound. Okay, so bell work fine. Cosine 1/2, sine 1/2, tan theta. Here's what I came up with. You're welcome to challenge this. Whoa, that's not what I wanted.
No,
Yeah, 5 pi thirds. So there's that, and then you've got pi sixths and 5 pi sixths, and then you've got 5 fourths and 5 pi fourths. Okay. So there's your solutions. Let's go ahead and get started here. So let me tell you a little bit something about bell work. I'll give you the answers. I'm not going to tell you how to do it. Okay? This is where you step up and say, maybe I'm hurting a little bit. I need to come see the teacher. Okay? Now, if you got it, then kudos. That just reinforces the fact that you know it. But if you don't know, oh, that's horrible. That's an ugly 6. But yeah, if you don't know, then you're hurting. This is some of the basic stuff that we did with the trick. So come see me, okay? Or when we have that independent time, then you can approach me at that point as well, right? Okay. Let's go and get started. That's too small. Can you guys see that? Okay. Today's purpose: we are graphing polar equations. Polar equations are fun. Okay. There are 2 ways. I prefer one of them. We'll talk about that. Objectives also posted over here. Our other objective. Oh, here's some of the stuff. We're going to use the old school method. Pick X, spits out Y type thing. We're gonna pick a theta, and it's going to spit out some coordinate as well. The other thing too is we're going to do some symmetry tests, and we'll talk about what that means and how they work. Questions on our purpose today? What's our only objective today? The main objective? Graph polar equations.
Why is your mouse going crazy?
Like that? Because I'm shaking it. Okay, language. Use some content-specific language today. We've got la maçons. I hope I said that right. It's in French. La maçons.
I thought you were saying something like,
You know that video?
No, that's it's French. It's la maçons. Then we're going to talk about, make sure that you understand what those are. Understand what rose curve is going to be. And then we have lemniscats. Lemniscats. I'm not sure if I say that correct. Lemniscats. Okay? So again, I don't mind you collaborating with your neighbors, but that's what we're doing. Thanks for closing those laptops. We are collaborating and not just having chit-chat conversations. Okay? You're professional students, yeah? Job. Okay. Wait. Toss them on the board over here. Booyah! I'm trying. Huh?
on the test, you're like saying, oh, what's this? You know how they do the vocab? They've done that on a QA test before, where it's like the vocabs in there.
Yeah, is this gonna have vocab gonna be on the test?
I don't know. I don't think so. But we need to know what we're talking about.
You don't take the test?
Not all of them. I'm on some committees, not all the committees. If I was on all the committees, I would live here.
Oh my gosh.
I would move my family into this room.
What test did you make? What test did you make?
Last year I was on Algebra 2.
So you made those tests.
Yeah.
Thank you.
Thank you.
Those were actually pretty like nice.
Thank you.
Those didn't hurt me too bad.
Tell you trust.
Yeah, who's on this committee?
Yeah,
So
who
I
is
know.
One of them's not here anymore.
You have to give them a certain time. Then why are they on that committee?
I will be on it this summer, okay? Commentate.
But I'm not
Good idea.
But we're not going to be here next.
Well, let's move on.
see.
Are we good here?
Yeah.
Good.
Yeah, I'm gonna be out of this campus.
Okay. Polar equations is an equation whose variables are r and theta. So we're not talking about x and y anymore. We're talking about
R and
R and
theta.
data.
Greg, you okay back there? You praying? Make it a good one. All right, so so they don't have x and y. They're going to have r and theta. And the way you graph them is going to be on this thing right here. And of course, I think some of you guys have already figured out that each one of those circles is kind of a unit larger than the last one. So you've got the unit circle on the very inside. Then you've got 2-unit circle, 3 units, 4 units, blah, 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 blah. Okay? Yes, you're welcome to draw that. with larger unit circles behind it. I shouldn't say unit circles because there's only one unit circle. A 2-unit circle, then a 3-unit circle, then a 4-unit circle. And they
It's
just
a unit circle with some radii.
and they just go.
Circles with different radii.
There are circles of different radii.
I got it right. Look at me go. I'm doing so good. You know, what? I'm not gonna draw that. I'm not because I don't know how to draw a circle.
Mine look like ovals.
You don't know how to draw a circle? Go like
Don't at me.
We need to like draw
Well, like,
a scale and
go like this. How you draw a circle?
Wow.
Believe it or not, Thomas. I knew that. I must have shown you that.
Okay, can I move on then?
No.
Oh, I have to leave. We're busy. Where would I take it? Doesn't make me feel good. No, I'm never that person. All right, cool. So, oh, sorry, like, switch this. Did you get your picture? All right, here we go. Thank you. So we talked about these two equations already. R is equal to A cosine theta and R equals A sine theta. Or were these the other ones? Are these new to you guys?
We've done these kind of.
They look very familiar, correct? But let's break it down and talk about it here. If you guys remember, A is your stretch, correct? Usually is. That is going to be the length of the diameter of your circle there. Okay, so here's the cosine version, here's the sine version. So if you want to think about it, A as the diameter of the circle, okay, that's really kind of helpful there.
I just spelled coordinate.
C-O-O-R-D-I-N-A-T-E-S. Oh, not plural. Take the S's. Correct. Correct. Coordinate. Forward. Anybody do this one? I remember this one. This is we used to do it. But now they do coordinate. Yeah.
Bob second.
Who? Bob Saget. Isn't he from Street Fighter?
No, what? What?
I wish like
What?
these lights could like be dim.
It's got a real nice pen.
I know. I called that.
Oh.
Abby Rose has its thorn.
Alright, see if I can get it working on 2 seconds.
Every rose has a thorn. Okay. Thank you.
Out of all spots.
Oh, my bad. I tried, Mika.
Wait, is it
I tried.
directly in the middle?
Okay, quick question.
What's up?
Why is the sign on the top of the cosine?
Well, think about it. Yeah, we're talking about cosines, right? What is? Let's start with some theta, like I don't know, pi.
Oh, pi over 2.
Pi over 2. Okay. What's the sign of pi over 2? Not sine, cosine. What's the cosine of pi over 2?
Zero?
It's 0, right? So pick a number for A. Let's go 1. So 1 times 0 is 0. There's your first coordinate.
Oh, that's fine.
Okay, and that's all we're really doing. We're just coordinate all the way around.
Oh.
Same thing for sine. Okay, and it just turned out that that's what it looks like. But it should kind of make sense, doesn't it? Because cosine is your side to side,
Yeah.
is your x-axis.
What turning?
When we talk about cosine, it's your x, and we talk about sine, it's your y. So it kind of makes sense that cosine circle be here, generic sine circle be there.
That does make sense, okay.
Okay, make the connection.
Is that an A that you wrote right there?
Yeah.
I wrote a what?
A, yes.
Oh yeah.
There you go, but I like
My circle looks like it has measles. Let me get rid of that. Measles.
Got second.
Okay.
My favorite movie is Love.
We're done with this slide? Okay, so next slide. Graph the equation of r equals 4 sine theta. For starters, super simple, what is the diameter of our circle in this case? 4. So our radius is
4.
2.
Wait.
half of that.
Oh, yes, 2.
2. Pretty simple stuff, right?
Yeah.
Okay, so what we're doing is we're going to pick specific points across 0, where'd it go? 0 to pi, okay, so we can try to get a general shape of this. Kind of like when you used to do your input-output tables. You guys remember those bad boys?
Yeah.
That's exactly what we're doing here. So here's our function, r equals 4 sine theta. some very important value to pick would be 0, correct? So if we're at 0, we're going to go 4 times 0. Where does 0 come from? The value of sine when it's 0. When sine is 0. Okay? And then we're going to do pi sixths. What is the sine of pi sixths? 1/2. That's where it came from. So 4 times a half is 2. So now we have the coordinate 2 comma pi sixths. Then we pick pi thirds. Here's our pi thirds. When we plug pi thirds in, we're going to get radical 3 over 2 as the sine of that. Right? And then we multiply it out. We get about 3.5. There's our other coordinate for that. That produces the coordinates. So they're coming in the form of r comma theta. That ordered pair r comma theta. I would just pick a few that I know, like your 30 degrees, your 45 degrees, your 60 degrees, your quadrantile degrees, all those different ones that you kind of know what they are, because they're going to be easier to come by. You're confused?
I don't get this. It's like started.
Hold on. No one gets left behind. Not this early. Not this early in the slide. Let's go plus here. Let's go back to, okay, we've got an empty one. Okay, so if you had, let's go y equals 3x plus 2. Remember that business?
Yeah.
Okay, what did we used to do? You used to pick,
3
some x's, and it would spit out some y's. So I could start with 0, right? So 0 times 3 is 0, plus 2 would give me 2. Remember this whole business? Okay, we're doing the same thing, the same idea with our polar equations. In this case, we had 4 cosine theta, was it? Or was it sine? All right, so 4 sine theta. So let me walk you through where some of these numbers come from, because I think that's where you're getting confused. It's not this part of it. It's what we did for the bell work. You see why I chose that bell work? Yeah. So, in this case, we're going to pick thetas. Sorry, that shouldn't be r. That should be x. That should be r. So we're going to pick some thetas, and they're going to spit out some r's for us. And what that'll do is create some coordinate pairs for us. Theta being the angle, correct. So, you could. So let's do this. If you can't think about it in 0 to pi, think about it as 0 to 180 degrees, okay? You can think about it that way. So, some numbers that I know, let's see here, I've got 4 sine. Let's start with the angle being 0 degrees, okay? Let's do this like this. Well, we have to use pi, but let's do it in, how about alpha degrees? So I'm going to do, for starters, 0 degrees. 0 in radians is still just 0, correct? Okay, so let's think about this. What is my sine value?
0.
Yeah, correct. Sorry, let's go back. So the sine value, if I go over here to 0, I don't move up or down, do I? So that means that all of this is simply 0. What is 4 times 0? So that's going to go here. Now, what's the next smaller one that I know? I know 30 degrees, don't I?
30 degrees.
30 degrees is pi sixths. All right, so I'm going to leave it this way. So let's do 30 degrees. Okay? So here's a 30. Opposite 30 is 1. This is a 2. This is a radical 3, correct? What is the sine value here? So what is it? 1 over 2. So 4 times 1 over 2 gives me, and there's my next coordinate. This is the first coordinate, that's the next one. Then I would go to maybe 60 degrees, right? Which is what? Pi thirds. And then I would find the sine of that. Well, the sine of 60, let me draw that real quick. Ooh, that was huge.
Understanding how you're triangle there.
This is radical 3, this is 2, this is 1. So that would give me 4 times radical 3 over 2. So that becomes 2 radical 3?
Wait,
Wait,
how do
hold
you,
up.
he can, I don't see that.
Don't see what?
How do you-
What's the sine of 60 degrees?
Can I multiply that to that? Like,
Well, 2 goes in here twice, right?
Hold up.
Multiply it. Do it. On your calculator. You do 4 parenthesis radical 3 divided by 2 close parenthesis.
okay, 3.4.
So it's approximately 3.5, right? That was the next number in our list. Oh, it's approximately 3.5.
Oh.
Okay.
That's all we're doing. Inputs, outputs, inputs, outputs.
Okay.
Old school.
But I like this.
Okay? Give me a thumbs up if you're good with this now. Give me thumbs down if you're not. I said thumbs, not heads. Thank you guys.
Oh, wait.
What's up?
So, okay. How do you determine what, like,
What you plug in?
yeah.
What you plug in where? Here?
Yeah.
Or what you plug in for sine theta?
For theta.
For theta? I'm going to pick the ones that I know. Remember the angles? The two special triangles?
It could be anything.
Yeah, technically. But are you going to pick stuff that you don't know the signs to? No, I'm going to pick 0, 30 degrees, 60 degrees, 90 degrees. Oh, I missed 45 degrees. So I would go 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And then I would keep going in those across the unit circle that I do know the signs for.
So, if this came up on a question, how would you properly answer?
It would probably be a sketch.
So you would have to.
So they would give you the polar
You would have to
grid, and you would sketch your image.
around the whole unit circle?
Yeah, pretty much.
Wait, so
Not the
that-
whole unit circle.
That means you're drawing a circle on the graph, right?
Hold on. What's up? You want to do it in radians because I will wait. This stuff is not getting easier. And the level of inattention is going up. Thank you. Yeah, legit question, and then I'll answer yours. What was yours?
So you're pretty much like, if this was to come up, are you graphing a circle?
You are graphing the circle.
So you're not, like, they won't ask, will they ask you, like, in different parts, like, what, like, the coordinate is? Or
They
you
might.
just have to graph it?
They might ask you for the coordinates, and then you'll have to spit out a few of them, kind of like what we did with our table. Or they might say, what's the graph look like? And then you have to be able to sketch it on that polar grid. Okay? Go ahead.
Sorry, and that's just me putting that.
Inputs, outputs, inputs, outputs. You graph them, and they should give you a general sketch, right? Whenever we did lines, did we graph like a billion of them to give us a line? No, we grabbed a few of them because then we know the general shape. We know what circles look like.
Yeah.
So then we just need a few, and we could be able to draw a circle around those. Okay? Now, for the math part, if you know them in degrees, good, but you still have to convert them to radians. Because the polar grid, next slide, is not in degrees. Degrees is something that is not really something that we can graph. I mean, you can kind of visualize them, but that's what it's going to look like. Okay? And there's your circle. Now, remember we said that? What was the diameter of our circle from the beginning?
Up there.
What?
I thought they were all around the origin.
No,
That makes sense.
not in this case.
You wasn't allowed to go up there.
Yes, it is. It's allowed to go anywhere. Go ahead.
So,
Well, I'm just asking about the degrees because let's just say it's like 146 degrees, then it'll go with radians. Like, would that still be possible? Or should
You can convert to, yeah, it can happen. Because technically, all of that is fair game, isn't it? So can I graph 146 degrees on this? Yeah, so I should be able to convert that into radians as well. Okay?
wait, so the radius is 2.
Yes. Did we not decide that already sooner? Earlier, I mean?
Yeah, but
I don't know. Just take the thing.
can you do another one?
No, why would I do another one? So, for starters, before we move on, notice that it is a circle, and its center is up here at, what is it, pi halves 2, or 0, 2 in this case. If we were to convert that over to our rectangular grid, here's that process, right? So we go r equals 4 sine, r becomes, let's see here, where we go? So we're swapping out our y's and our x's. Combine it all, you're going to get this bad boy. Remember we talked about that as well when we had the vertical shifts?
Where
For-
did sine go?
Sine became, what's that conversion, guys? Was it r theta is sine or x? It was from yesterday's lesson. Let me grab it up real quick.
Sunday's lesson.
Because,
I can't remember last week. Wait, what was yesterday?
well, not yesterday.
Yesterday.
Oh, like the X and the Y?
Correct.
Oh, okay.
I just gotta go back.
How
and
did
look
the
at my
X
notes.
get on the other side?
I'll do that.
Oh, because R is X squared plus Y squared.
Yeah, so x is equal to r cosine theta, and y is equal to r sine theta. So all of this became y. We switched it back, and then we know that r squared from Pythagorean's theorem, or even the circle formula, that r squared is equal to x squared plus y squared. Once you clean all that up, you're going to get your rectangular old school way, which tells, oh, this is we're just working with a
so much
circle.
easier.
Yeah.
I
Can't
But-
I do that?
Well, you can use that to verify.
Well,
You can do
come on.
that to verify,
Why can't you do it to just do it?
because that would be rectangular. And what are we working with? Sorry. Polar equations.
Oh.
And polar equations go on the polar graph. Okay?
I don't like it.
It's different. It's very different, right?
No, it isn't.
You've taken my rectangular and you've made it circular. Now, pretty cool stuff.
Wow.
Okay, so some tests for symmetry. Here's your first test. I kind of separated these to kind of try to make them a little bit bigger for you. If you have symmetry about what we call the x-axis, which is technically that line that goes across from 0 to 180 degrees. So symmetry across this line, we're going to go ahead and call it the x for now. If you replace your angle with a negative angle, and the equation still comes back the same, then you have symmetry about the x-axis. Now, please do not try to use the same rules as we did before with polynomials, because you will be wrong.
Wait, can you show like,
I don't know, polynomial.
I don't understand.
Can you
like,
like
can you show
explain,
it?
like show
Like,
us,
give me an example.
Yes, I would love to.
Like with the variables, not the.
So let's talk about, if you think about the bell work, how many solutions did I get? I got 2 for each one, didn't I? Because there's 2 possibilities. So let's say I was talking about, what would a formula look like? R is equal to, we'll just do cosine 30, okay? Cool? So I've got cosine 30. Technically, what is the cosine at 30?
1/2,
Yeah, no, it's not 1/2. It's radical 3 over 2. So technically, there's my equation, okay? And I'm gonna look at it this way. So let's take this. Let's go r is equal to cosine, but now it's not 30. It's going to be negative 30.
Oh, and it's
So I've changed my positive angle with a negative angle, correct? Let me find out what the cosine at negative 30 is. Can you guys tell me what the cosine at negative 30 is?
square root of 3 over
It's still a positive square root of 3 over 2. Has it changed? No. Therefore, this has symmetry about the x-axis.
So if it's equal, the graph is.
Right, so here's what I'm really checking here. Did this piece of it change? When I put a negative in there, does it really change at the end? And in this case, it didn't, did it? So I've got symmetry about the x-axis.
So, okay, wait, that makes sense, cause like whenever when we're doing the phone thingies, you don't remember talking about like how if it's positive you go that way, if it's negative you go that way, right?
Correct.
And so, cosine always gonna be positive here.
To the right, correct.
Right.
Okay. I think I'm gonna have to go home.
Me too.
Or taking a power nap or something.
I know, I feel super light.
Let's just do that right now.
Hey, heads up. What does it say? Heads down, thumbs up. We're no captains. Nobody picks anybody. Okay.
Oh wait, no. I do.
Okay.
Still been on straight.
Thank you.
Oh, what is when you gonna shave your beard?
You're very when you were in high school, did you take like did you take a math class? Like in high school, like did you take like calculus and stats and stuff?
I took calc and pre-calc together.
Together?
And I actually did better in my calculus than my pre-calculus.
How?
Not all of us are born that way, Munoz.
You're like, sorry, I'm a little bit too advanced.
No, I wasn't. None of it made sense until I got to college.
That's literally
My,
gonna be
my brain wasn't ready.
But
I
you're
really
pretty good in
probably still won't understand
calculus.
most of what Mom says.
Yeah, because I can follow the
It still won't
rules.
make sense.
Yes. I don't know what it was.
That's what Mr. Althoff said his son.
But here's what he did. I had an A in calc, I had a C in pre-calc, and he averaged them both and gave me B's for both.
No.
I was like, not cool, bro.
Was it the same teacher?
Yeah. We only had one teacher that
That's
did
the
the
thing.
advanced
If
stuff.
you're doing great in like calculus, but not great in pre-calculus, you're like, oh, if you're doing like have an A in pre-calculus, you have an A in pre-calculus. Like that's fake. Those are fake. But I guess it's better than we what do you feel about statistics?
I love statistics. That's my baby. Oh, here it is. Okay. Hiya. Next slide. You guys ready? Here's my next slide. Now notice they don't call this the y-axis. Oh, actually they kind of do. Never mind. So the axis that goes up and down. I didn't see y on my notes last time. Do you have this type of symmetry? For this one, you have to replace both r and theta with negatives. Remember before that was the origin symmetry? But not for this one. For this one, you're changing both of them.
So it depends on the quadrant.
No, it depends on what type of symmetry you're looking for. You can test anything for that type of
Still
symmetry.
looking for cosine in this one?
In this case,
Cosine symmetry? Or sine?
no. Cosine was my example. Cosine was my example, right?
Why is it different?
Why is what different?
Is it because it's in the top left quadrant that they're both negative?
I'm not sure I understand your question. Reframe it one more time.
So in the first quadrant you have r and regular theta, and then the fourth quadrant you have r and negative theta, and then the second quadrant, why do you have negative r and negative theta?
Because that's how I'm going to check if you have y symmetry.
But wouldn't it so if it's in the second quadrant, it has to be negative r and negative theta?
Yeah.
Wouldn't it be
We're not in the third quadrant.
That's the second. I said the second quadrant.
Okay.
It has to be negative r and negative theta.
Well, let's agree to this first because it's kind of. Let's think about the sine function, okay?
Okay.
The sine function. Let's do this one. Let's do 30 degrees again, okay? Because we seem to be doing okay with that one.
Yeah.
So I would have this angle here, which is 30 degrees. This would be 1, 2, radical 3, correct?
Yeah.
So I have, what I'm asking for here in this case would be, let's leave that as 1. Let's go sine of 30 degrees, okay? Just like we did with the cosine, okay? So if I have sine 30 degrees, what is the, yeah, so r would be 1/2, correct?
Yeah.
So what I want to do in this case, now do you agree with me that the sine value would be the same here if I put an alpha prime of 30 in here?
Yeah.
It would still be 1 over radical 2, right? Or sorry, 1 radical 3 and 2. So the signs would be the same. That's kind of what we're testing for, to see if that's true. Now, they're not always as obvious as the sine or the cosine was in the last example. So what we can do algebraically is we can change. So let's give this a value. This would be 2, correct? Or r would be 2. So let's see here. Let's change them. So I've got negative 2 is equal to sine negative 30, correct? So for starters, this is my negative 30. But what does this negative 2 do?
Graph it in the
In the opposite direction. So there's my negative r, negative theta that I'm comparing to. And we agreed that, yeah, if that is true, then we do have symmetry about the y-axis, don't we? That's why you see 3 lines. One is for the angle alone, and the other one gives me the angle and the radius.
I'll grasp it.
Just intuitively, does this have symmetry about the y-axis?
Yes.
Well, you don't know. Well, sure.
Does it? Okay. Well, you're saying that if I went this way and put a 30 degree in here, what would the values be? 1 Wait a minute, what did we use before? Okay, we used the 30. So that would be 1. This would be negative radical 3. This would be 2, correct? Now, what is the cosine in this case now? Negative radical 3 over 2. Do those match?
No.
Therefore, you don't have it. So I can test that same symmetry that way, but there's some rules that have to apply.
So when do you?
Go ahead.
I'm thinking. I don't know how to. I think.
We'll do an example right now. Maybe it helps.
Well, like I got it. Like I know what you're doing. It's just when I have to do it myself, I'm not gonna understand.
Well, here's what you're going to do by yourself. If it asks you to check for symmetry about the x-axis, then you're going to take your angle and you're going to make it a negative. So if I have r equals a cosine
Okay, so if,
something,
if you're checking x, then you just use the.
you're going to convert this to be a negative angle, and then check if you get the same thing out.
And then if you're checking.
And if you're checking for
y,
y,
the r.
you change both of them. You change both of them. So in this case, if I have some angle, let's go r equals a trig of something, theta, I'm going to change both of them and check if I get out the same trig equivalent. Okay?
So you're checking the y-axis, you change the r and the theta to negative, and
Correct.
you're checking the x-axis, only change the theta to negative.
Correct. What if we want to check for,
That's what I was asking.
and then we have one more, which is respect across the origin.
There's another.
Well, they should make sense to you. If I want to check origin, then
Okay.
the only one that should change is r in this case. You should have seen this one coming. Connected with looking at the other symmetries.
I was like, why is this here?
Because if I go in the opposite direction, then and I get the same thing, then I should have that symmetry across the origin.
I got it.
Okay, this is kind of like our tan example, right? Yeah, so the perfect example of this one would be tan. That's not helping.
See, Munoz, I think what made it like tiny weird was, see how, because we're just like looking at the, how the quadrants go, so it's like positive, positive, and then third quadrant is even negative, and it's not. I don't like it. Like, I understand.
Wait. What would it look like if it did have y?
If it did have, then you'd be looking probably at a sine of some sort. Because sine has symmetry on y. Because remember, they're both positive going up, correct? The radius is always the radius. And when you're looking at some kind of cosine one, then it might have some type of x symmetry. And if you're looking at some origin symmetry, then you're probably looking at a tan function of some sort. Alright. Let's put this into practice.
Okay.
Let's check for all symmetries on this function. R is equal to 1 plus cosine theta. R is equal to 1 plus cosine theta.
And you have to put a random angle in there.
It's going to be up to you. Yeah. If you want to do a random angle, that's fine.
I need to update my game like
Okay, Munoz.
I don't know.
Maybe we open the door.
you got a tree, like one of those trees out there, you grab the leaves or just like seal it with mush or something. Ask them like the sprinkles are like
Did it sprinkle already outside? It's supposed to rain out like right after school.
How long are you here after school for when you do tutoring?
I'm here for an hour. Mr. Rawls is here for the other hour. So
Are you gonna
there
be
is
here
2
tomorrow?
hours.
Oh yeah, are you gonna be here tomorrow?
Yeah.
Oh yeah, I can't do this.
I don't know. I'm not even sure right now. Depends on how I feel now.
Okay,
But I am scheduled to be here.
because I want to retake chapter 5, but like I need help with a few things.
Unless
And
like
I
you got some
don't think I can see after today.
Okay,
Are you here tomorrow?
credit goes in totally higher. Just like
What's up? Oh,
Eric has to send
I see what you know. That's correct. Can I assume that he puts the captcha? Oh, I thought you wanted to leave and say, oh, you say share right here. I was trying to do the emoji.
Actually, my hand is you.
Heart.
You should have just got around it. You can't even face your
Ah, that's funny enough. I see what you did there. Okay. Do you see the solutions already visually? In your mind's eye? Does it have X symmetry?
I didn't make the R yet.
Yes. Does it have Y symmetry?
I don't know how to check out what do you do with the R?
Does it have symmetry about the origin?
I don't know.
I picked 90 degrees. How do you do that?
Why did you pick 90? That's a horrible one to pick. Anything other than quadrantiles. All right, so for starters, let's see here. If I did R is equal to 1 plus the cosine of some angle, I'm going to pick something like simple that I know, like 30. I can always count on that guy. What's the cosine of this guy? What is it, radical 3 over 2?
Yeah.
Okay, so I got radical 3 over 2. Let's go ahead and switch it for now. 1 plus the cosine at negative 30 degrees. That would still give me a positive radical 3 over 2, correct? So did they change?
No.
No, so we do have X symmetry. Okay? Let's try.
Wait, hold on one more. Okay, we're good.
Here's my positive 30. This is 2, radical 3, and 1, correct?
Where did the 1 go?
It's still right there.
So how do you?
All I worried about was this part.
Oh.
And then I did the 30 degree one. This is 2, this is 1, or negative 1. This one's a positive 1 here. So if I found the cosine of this negative 30, it's still going to be radical 3 over 2. So they didn't change. All I want to know is if they're going to change or not. And in this case, they really don't, do they? Okay? Now, checking. So let's see here. X, good. Y, don't know. And then origin, I don't know. So let's see here. Which one do we want to check next? Y? We're going to have to change both of those. So we had R is equal to 1. Let's pick an R in this case. Let's pick an R in this case. We know that it's a 2, right? So we'll go 1 plus cosine. We're going to do 30 first. We'll do 30 first. And then for the check one, we'll do negative 30, okay? So here's my triangle. Here's 30. 1, 2, radical 3. Okay? So there's that.
Why'd you put the 2 there?
Say that one more time.
Why'd you put the 2?
Because I need a radius. I need an R. No, it's right there. It's 2. This is a 36.
Oh, yeah. I was like,
Okay? Now, we're changing both of them. So now I got to go. Negative 2 is equal to 1 plus the cosine at negative 30 degrees. Okay? So let's do this first. My cosine at negative 30 is here, correct? But that negative 2 is telling me I got to go the other way. Right? So, does this have the same cosine as my original one? In this case, it's a negative radical 3 over 2, correct? So my formula has changed. So this does not have Y symmetry. Okay?
Oh, you're looking at the sorry.
No. Question, ask me. Were you okay with the cosine one?
Yeah.
But not this one. Okay. So,
Oh,
Wait.
hold on.
R can never be negative. I thought like the
No, remember, the fact that it be negative just means you're going to go the other direction. Yes, you're correct. So let's talk about this real quick, okay? So, are you okay with this piece of it? My radius is 2, the cosine, I'm going to find all that good stuff. So here's technically what I have. 2 is equal to 1 plus radical 3 over 2, correct? Are we good? Okay, so I need to test negative r is equal to 1 plus cosine negative 30. Okay? There's my positive 30. Let me sketch my negative 30. Negative 30 degrees means I'm going to go this way. Correct? And this r being negative here is telling me that I'm going to do the other part of it in the other polar direction. Okay? So this dotted line is my triangle, technically.
What are you setting that equal to? Like
Setting what equal to?
So when you found the cosine of that, the one in the second quadrant, and you get negative square root.
It's a negative 2. But that doesn't tell me that this length is negative 2. It's still 2, right? Go ahead. I'll get to your question next.
If you find the cosine of that triangle that you just drew in the second
The solid or the broken?
the broken one,
Okay.
then it's negative square root of 3 over 2.
Correct.
What are you comparing that to? What are you comparing the negative 3 over 2?
To the original one. Oh, here it goes. Sorry.
Oh, okay.
Now, do those look the same?
No. Well, but the negative 2.
All the negative 2 is telling me is that I went the polar opposite. So even though this was the angle here, I really want to go in the polar opposite and get this triangle
Okay,
there.
so if the r is negative or positive, that doesn't matter?
Well,
Like,
this
in
will.
the end result is
Here it's not going to be a negative 2. It's still going to be a positive 2 because distance is positive.
yes.
This is just to tell me, hey, I went in the polar opposite direction to create my triangle.
So when you're comparing the two equations, like the 2 equals 1 plus square root of 3 over 2, and the negative 2 equals 1 plus square root of 3 over 2, the negative 1, you're only comparing the cosines?
In this case, yes, because it's a cosine function.
So like the 2 being positive and the negative 2 don't like correlate? Like it doesn't matter if they're different. Like if okay, so if you
Yes, they have to be. Well, in this case,
the
if they were.
bottom one came out square root of 3 over 2 without the negative, but the negative 2 is still there, does that mean it didn't change? Because like you're just using the r's.
So let's talk about this real quick. Are you okay with why this came out?
Yeah.
Okay. Now, do they look exactly the same?
No, but that's what I'm asking. Like if the 2's
Let's say this was positive.
yeah.
Would they
that's-
still
yeah,
look
that's what
exactly the same?
No, that's what I was asking.
It's still
If
so
the
then it's
2's
still a
if the
no.
2's
So
better-
regardless, it changed. Even if this one changed or this one didn't change, it changed. They're not the same. They have to be the same.
But you have to make the r negative.
Correct? So even starting with that point, I know it's not going to match my other one, right?
Yeah. Then doesn't that mean they're all gonna be? They're never gonna be symmetrical if the r has to be negative to check it.
No, not necessarily.
What instance would it be? Would it be right?
If it was
Let's
sine,
see here. If we're doing sine, yeah, in sine. If the r changes, it will still the same thing.
so yeah, but that's in sine though. This is cosine, so in cosine it's never gonna be like.
No, and that's what I was trying to say a minute ago, right? Usually when we think about having x-axis symmetry, we're going to be thinking cosine.
So.
And it's not going to have any of the other two symmetries. Which one's going to have our y symmetry?
Oh,
Sine.
sine can
Which is
never
going to have our origin symmetry?
Can they all have all
Can.
No.
No. Okay, so they can only have like one symmetrical.
Unless we graph and then move it around, translate it in such a way that yes, our circle does have that symmetry.
That makes sense.
Then-
That's
then
what
yeah,
I was
then
asking.
probably-
That's what I was
So
asking.
like can be symmetrical to the origin?
Correct.
So checking these like
Yo,
just making
10.
sure for a fact like
1
oh
plus the 10
see if
theta
it's
is so
gonna be
weird. You graph it
symmetrical
like
or the y axis but it's not completely. We're gonna just check it
You
anyway.
you want to check it anyway. You want to be able to go through the process. Okay, I'm going to try to get through the rest of this. Good conversations. Where are we at? Check this out.
There's marks in the circle.
Yeah, these are cool, right?
No, they look like bugs.
These are called limaçons. Limaçons. We're not going to. We already shown you how to plug in some values for theta, spit some numbers out, and sketch that way, right? This is what we're going to use most of the time to graph those for us. So I want to show you. For starters, on your calculator, you're going to want to change the mode and go from being a function to being a polar function. So we're going to go over to polar, and then that's going to change our y equals value. Okay? What was our function? It was 1
plus the cosine of theta.
plus cosine of theta. Theta is just our x value, and it'll put theta in there for you. No more x. Now it's theta. Cool, huh? So I'm going to close this. I'm going to go zoom 6, which is my standard screen. Now, I want to point out that it doesn't look exactly right because our polar has to be squared, doesn't it? It's got to be squared off. This is stretched. If you go to zoom again and you select squared, it's going to square it off for you, and you're going to be able to see that function a little bit better. And if you can't see it still, then zoom in. Zoom 2. And there's our limaçon. Now look at the image. Does it have y symmetry?
No.
Does it have origin symmetry? No, it only has x symmetry.
It looks like a bee.
It's more like a leaf. Okay, so let's move on. These are called Rose curve.
That looks like a butterfly.
You can graph those, play around with those. Just something to notice. Usually when you have even, if you're, you guys see that 2 theta in there?
Yeah.
Usually when you have that, you're going to get double the amount of leaves. So notice 2 gives you 4 leaves. When it's 4 here, you're going to get 8 leaves, petals. But usually when it's odd, that's the number you get. So 3, you get 3, 5, you get 5. So just something nice to look out for. Oh, these are not functions anymore. We're not even on the rectangular system anymore. We're in polar functions, right? Okay. So these are Rose curves. And again, you can plug in values and spit them out if you want to sketch it primitively. And then I want to show you your Lemniscats. Lemniscats look like this. Okay. And you can always throw them into your. Is it Lemniscats?
No, it sounds like lemon skips.
Oh, lemon skips.
That just makes it easier.
Wow.
All right, so go ahead and do that.
Do what?
Oh, you
Sorry.
your data equal to.
Do them on your calculator is what I wanted to say.
Look at when you
So you take a sketch, make sure that you're doing the square.
shows you your theta.
What?
It shows you the degree.
Okay.
Yeah, Munoz, I think
I think I just came down with something that.
I just saw like